In this video, we're finding the definite integral of sine pi x cosine pi x on the interval -1 to 1. And the point of the video is to approach this integral like a physicist. In other words, we're going to try to exploit every symmetry that we can find to simplify the work rather than just using brute force to guess the antiderivative and all that. So there are actually two different viable symmetry approaches to this integral. And the first one involves thinking about function parity. In other words, the evenness or oddness of functions. So the sine function we know is an odd function, and the cosine function is an even function. And we also know the product of an odd and even function gives us an odd function. So if you have no idea what I'm talking about, I'll post links to my videos on even and odd functions up at the top of the screen. But the conclusion here is that if I integrate an odd function on an interval symmetric about the origin, then I know the result has to be 0. And this is because odd functions have a rotational symmetry about the origin. So let's bring in a graph and see what that looks like. So in our graph, we see that odd symmetry to sine pi x cosine pi x. If we use the origin as a rotation axis and we just rotated the graph 180 degrees, we get a copy of the original graph. Well, what that guarantees is that on a symmetric integration interval, you're always going to have just as much positive area as you do negative area in your integral. And those positive and negative areas cancel out, and you're guaranteed to have your integral vanish. Now, this graph brings up a second type of symmetry method we could have used to solve this integral. We notice in the graph that sine pi x cosine pi x actually turns out to be a simple sinusoidal function. And to figure out how this works, we have to use a trig identity. So consider this physicist answer to the integral number 2. So we remember this trig identity that has to do with a sine multiplying a cosine. So we have sine 2 theta is equal to 2 sine theta cosine theta. That means anytime we see a sine times a cosine, we can rephrase that in terms of a sine of twice the angle. So what we're going to do is divide both sides by 2. And we see that sine theta cosine theta is 1/2 sine 2 theta. So let's rewrite our integral. So we've rewritten it as the integral from -1 to 1 of 1/2 times the sine of 2 pi x. Now the period of sine 2 pi x is just 2 pi divided by the coefficient of x, which is also 2 pi. So we find a period of 1. And this means in our definite integral, we're actually integrating over 2 entire periods of this function. Well, anytime you integrate over an integer number of periods for a sinusoidal function, you're guaranteed to have the areas cancel out again. And we can see that in our graph. I cover the first period of our function from -1 to 0, and this positive area cancels this negative area exactly. So anytime you go through a whole period of a sinusoidal function, this is going to happen. Then we just integrate through another period, and those areas cancel. And it's just another way of finding out that our integral is 0. So there's a couple good lessons in this example. Anytime you see an integration interval that's symmetric about the origin, go ahead and investigate the parity of the function you're integrating. If it turns out to be odd, you have an easy 0 for your answer. And then second, anytime you're integrating a sinusoidal function, go ahead and check whether or not you're integrating on an integer number of periods. And that's another way to find out you have an easy 0 for this solution.